Hey there, and welcome to this explainer. Today we're going to pull back the curtain and uncover the invisible regulators that are quite literally running our everyday lives. From that simple toaster sitting on your kitchen counter to massive, sprawling industrial manufacturing plants, there's this hidden, absolutely brilliant logic at work, humming away in the background, keeping our chaotic world perfectly in check. It's fascinating stuff.
To really ground this in reality, let's just consider a deceptively simple problem for a second. How exactly does a car maintain a perfectly steady speed when you're cruising down the highway on a hilly road? Or think about a massive industrial water tank. How does it know exactly when to stop filling just a fraction of an inch before it overflows? I mean, it almost seems like magic, right? But it's not. It is pure precision engineering. So here is our roadmap for today. We're going to start with the basics of control, then compare open versus closed loops. After that, we'll take a look inside the famous PID controller, talk about tuning for system stability, compare classical and modern control theory, and finally wrap up with automation and PLCs. All right, let's jump right into section 1, the basics of control.
At its absolute core, a control system is simply a way to manage physical behavior. Whether we are talking about a basic thermostat regulating your domestic boiler at home or a highly advanced flight computer guiding a supersonic jet, the ultimate goal is exactly identical. The system is constantly, endlessly comparing the set point, which is what we actually want it to do, with the process variable, which is what the machine is currently doing in reality. It's a constant game of catch-up.
Moving on to section 2, open versus closed loops. Now, there is a massive, game-changing difference in how these systems actually operate in the wild. Open-loop systems, they're essentially blind. Think of a standard washing machine or old-school timed traffic lights. They just run through a predetermined, rigid cycle, completely and utterly oblivious to what is actually happening around them. Closed-loop systems, on the other hand, are smart. Take the cruise control in your car, for instance. It uses continuous sensor feedback to monitor your actual speed, and then it physically adjusts the engine throttle in real time to match your desired set point.
Which brings us to section 3, inside the PID controller.
So how does that feedback actually get calculated? Well, this breakdown right here gets to the absolute heart of the system, PID. That stands for proportional, integral, and derivative. Let's break it down. The proportional term, that reacts right now. It provides an immediate, punchy response based purely on the size of the current error. The integral term, however, looks at the past. It works to eliminate that lingering, annoying, steady-state error over time by continually nudging the output until it hits the exact mathematical target. And finally, the derivative term looks ahead. It actually predicts the rate of change to slow down the system as it approaches the target, gently pumping the brakes, so to speak, to prevent the whole thing from overshooting. It's a brilliant balancing act.
But, here is a really fascinating industry secret for you. Most real-world processes completely drop that highly advanced derivative term. They just run with P&I. You might be wondering, why on earth would they do that? Well, because predicting the future requires flawlessly clean sensor data. And out in a real factory, which is filled with heavy vibrations, dust, and electrical noise, that sensitive derivative term can actually cause the machine's logic to totally freak out. So the simpler PI controller is really the reliable, true workhorse of modern industry.
Let's move to section 4, tuning for system stability.
Okay, so you have your controller. Now you have to teach it how to behave, right? There is a really complex mathematical science to this, for sure, but out on the factory floor, the most widely used tuning method is simply trial and error. It's a highly measured, practical approach. You start with a very low proportional gain, say 0.1, and you completely turn off the other settings. Then you incrementally double that gain, pushing the system harder and harder until the machine just begins to physically oscillate or vibrate. And once you find that critical breaking point, you pull back. You cut the gain in half to ensure you get smooth, stable operation without those wild, potentially destructive oscillations.
And honestly, plotting out the response shows us exactly why this manual tuning matters so much. When you're setting this up, you might initially crave a super fast, aggressive response to get the machine to its target as quickly as possible. But if you do that, you often get a dangerous overshoot before it finally settles down. Just think about the real-world consequences. If that overshoot means overflowing of that of hazardous chemicals or crashing a multi-million-dollar robot arm into a wall, you have an absolute disaster on your hands. In reality, you almost always have to tune the system for a slightly slower response because it's infinitely safer. Now, to guarantee that safe response mathematically, Engineers will map out the system's stability using what's called a root locus S-plane. I like to think of it like mapping out the physical boundaries of a roller coaster track. If the perfectly safe, smooth path we want doesn't actually exist natively in the machinery, we don't just give up. We mathematically force the system's hand by adding compensators. We are quite literally reshaping reality to make the physical system behave exactly how we dictate.
All right, Section 5, classical versus modern control.
It's kind of wild to look back and see how this has evolved. The leap in complexity over the last few decades is just staggering. Classical control theory, the stuff from the 1940s, tackled relatively simple single-input loops. Engineers were literally using paper, pencil, and Laplace transforms to figure this out. But modern control, that is a whole different beast. It operates in the time domain, utilizing complex linear algebra and state space models to handle multiple input, multiple output systems, often called MIMO. This is the heavy-duty advanced math required to do things like simultaneously steer the thrusters, adjust the flaps, and read the sensors of a spacecraft in orbit.
But here is the kicker. Despite all that modern mathematical firepower we just talked about, classical PID controllers still absolutely dominate global manufacturing today. And the reason for that is incredibly pragmatic. They are just physically easier to implement. But even more importantly, they are easily understood by the technicians on the ground. When a line goes down and someone has to maintain or tune a machine at 3 o'clock in the morning, you want something robust and comprehensible, not a linear algebra nightmare.
Let's wrap things up with Section 6, automation and PLCs.
So how does all this math actually survive in a factory? Well, instead of using fragile desktop computers that would honestly break down almost immediately in a factory setting, the industry uses PLCs, or programmable logic controllers. These things are essentially incredibly rugged digital brains. They're specifically built from the ground up to withstand intense heat, relentless mechanical vibration, and thick industrial dust. They're typically programmed with a highly visual language called lateral logic, and their whole job is to tirelessly execute our PID calculations and keep the assembly lines moving flawlessly, 24/7. When you finally combine all these elements, the sensory feedback, the precise PID logic, and the sheer ruggedness of PLCs, you unlock the holy grail of industrial automation. And it's really important to remember that it's not just about greedily cranking up production rates or slashing operational costs. Most importantly, this technology completely removes human error from highly dangerous, repetitive tasks. It keeps workers safe while ensuring perfectly consistent, relentless control over the machinery that builds our world.
As we close out this explainer, I want to leave you to ponder one final thought. Today, we've seen just how elegant, reliable, and resilient classical PID controllers truly are. But with the breathtaking rise of artificial intelligence, advanced neural networks, and evolutionary computing bleeding into automation, you have to wonder, will these tried-and-true classical control loops survive the next industrial revolution? Or are we fast approaching a day where our machines will simply learn to tune themselves? Thanks so much for exploring the invisible regulators of our world with me. I'll catch you next time.